So in the last videos, we considered a model of theory confirmation and a model of theory disconfirmation, which we decided was overly simple. According to the model of confirmation, you start with some set of, you first identify some set of observations such that if you were to get them, they would logically imply a theory. You then go out and see if you find them. If you do, then you conclude that your theory is true. And for disconfirmation, you start with a theory and say, here's some observations that it logically implies. Then if you fail to get those observations, you reject the theory. So scientific confirmation works by modus ponens and disconfirmation works by modus tollens. And we said this is implausible because any theory is logically consistent with any set of observations is logically consistent with multiple theories. So you're never going to be able to say, given this set of observations, this particular theory must be true, because there will always be other theories that are consistent with that set of observations. And the model of disconfirmation fails for a similar reason. Any theory is logically consistent with any set of observations, so it's never the case that a theory implies a set of observations, because if it were, then upon failing to get those observations, you'd be rationally required to reject the theory, otherwise you'd be violating modus tollens. But as we saw, there are always other rational moves to be made, that is, moves other than rejecting the theory that are available upon making a set of observations. So, this leads Quine to endorse what he thinks of as a kind of holism about theory confirmation. So theories don't face the tribunal of experience as a corporate body, they face the tribunal of experience as a corporate body, not as individuals. And basically what he has in mind is that you kind of confirm and disconfirm everything all at once, all the time, against all observations. And the question is, how can you do that? And that's what we're going to consider in this video by looking at what is these days the dominant view in philosophy of science on how theory confirmation and disconfirmation works. And here's the model. Ultimately, what we want to know is how probable a theory is. But when we're doing scientific reasoning to figure that out, what we really need to do is establish how probable a theory is given some observation that we're making right now. So we are making some observation, we want to know how probable is this theory given that observation. To put it another way, we want to update the probability we assign to the theory based on the observation that we're making. And remember, this is read as given that, the probability of the theory given that you get this observation. In order to do that, there's a few things we need to know. One thing we need to know is the range of competing theories. Now, as I mentioned in class, it's really hard to figure out how we go about constraining the range of competing theories. That is, we typically don't consider every logically coherent theory. In fact, we really never consider every logically coherent theory. Sometimes we kind of do, because we are going to consider a theory and then the negation of that theory, and we kind of throw all other theories into the negation of that theory. But we certainly don't typically list out theory 1, theory 2, theory 3, theory 4 until we've listed out all coherent theories and then sort of like consider all of them. Instead, we work with a constrained range of theories that we take to be somehow the privileged range, the range that we think are actually worth considering. How we do that? Pretty mysterious. There's interesting writing on that, but we're just going to set that aside. We also need to know how strongly each theory predicts the evidence, and we'll talk a lot more about what that is in the coming video. We also need to talk about how probable each theory was before we observed the observation at issue presently, that is, the observation we're looking at right now. And we also need to know how probable the observation is. Now, part of my goal with this sequence of videos is to have you understand why it is we need to know these three things to figure out the probability we should assign to a theory given some observation. So why is it that we need to know how strongly each theory predicts the evidence, how probable the theory was before we made that observation, and how probable the observation is? So I want you to see why you can think each of these is important for establishing that. And then we also need to know how to put all this information together. Okay? So this thing here, how strongly each theory predicts the evidence, is called the probability of the observation given the theory. This thing here, how probable each theory was before we made the observation, is called the probability of the theory, or the prior probability of the theory, that is prior to the observation. This is also called a likelihood. This thing here is the probability of the observation. Okay? So we need to know the probability of the observation given the theory, the probability of the theory, and the probability of the observation in order to figure out the probability of the theory given the observation. Now, first thing to notice is that this thing here is distinct from this thing here. So to see that, here's an example I used in class. What's the probability that someone is a sister given that they're a sibling? Well, it's 50%. So if I observe that you're a sibling and my theory is that you're a sister, I should say the probability that my theory is true given that observation is 50%. What's the probability that someone is a sibling given that they're a sister? Well, that's 100%. So you can see that the probability of the theory given an observation is not the same as the probability of the observation given the theory, because where the theory is that X is a sister and the observation is that X is a sibling, this one up here is 50%, but this one down here is 100%. So they can't be the same thing. Okay. Somebody asked a question in class, which was a good question, and in response I sort of illustrated. This thing here is similar to the conditional that says O arrow T. It's similar in the following respect. If the probability of a theory given an observation is 1, then O arrow T is true. If the probability of an observation given the theory is 1, then T arrow O is true. Okay, so now we want to know why we need each of these elements. And I'm going to stop this video there, and in the next video we'll consider why we need each of these elements.